Welcome to my YouTube video, which is dedicated to the learning of applied mathematics in civil and structural engineering. In this video, we will talk about simple mesh generation of 3D surface structure for finite element analysis. When I was a student at university, majoring in structural engineering, at that time, I want to build my own program for mesh generation of 3D surface object. But at that time, I did not manage to do it. A year ago, one day when I was watching my kids playing Rubik's Cube, suddenly I get the idea that actually Rubik's Cube concept can be used as a basis to build a mesh generation for 3D surface object or even solid object, as you can see from this picture on the right hand side. So this video, I will show you the idea of the concept. The basic idea actually is very simple. We start with defining the cubical blocks needed. So let's say how many blocks needed on the X direction, Y direction, and the Z direction. S here stands for short, W stands for wider. So you start the numbering from the short span and go through to the next wider span. The reason is if the numbering start from the short span, then you have a smaller, or you reduce the bandwidth for your stiffness matrix when you doing the calculation, building your stiffness matrix for the structure. And then apply or decide which rock that need to be removed as a void, because this is the basic foundation to model the real structure. Let's say there's a hole opening, then you need to set it as void. Then if necessary, you need to merge a side of the block to form the curved surface. I will show you with the example. So a simple example for illustration of the method. Let's say we have a 9 blocks, 3 on the short span and 3 on the wider span. In this case, it's the same 3 by 3, and 1 block for the Z axis. And we can see that block number 1, 3, 5, 6, and 9 are set to block. So we only have this block. And then to form this model, we need to merge the side from this side, the left side of block 2 with the bottom side of the block 4. So now we need to identify the sides of the block to be merged. As I mentioned that here, the side of 2 and 6 will be merged with 5 and 6. So at the end, the point 2 and 5 will be together, will be the same. And the same for this side and this side and this side. And the X represent a void. So if you see from the top, you will get this block number 2, block number 4, block number 8, block number 6 after removing all the void block. And this is the view on the vertical, on the Z axis, Z equals 0, and this will be Z equal 6, the top plane. Now we need to actually provide or calculate the actual coordinate x, y, z of the real 3D surface object. So here you see node number 2 and 5 are together, 3 and 8 together, 9 and 4, 14 together. And then we calculate the real coordinate, actual coordinate for the object x, y, and z for node number 2, 3, 6. And remember, you don't need to provide the coordinate that's not used, like coordinate for nodal number 1, number 4 is not needed. And then we need to identify which node are actually the same. The higher node number 5 is equal to the lower number node 2. So you need only to provide only one. Node number 2, 3, 6, 7, 9, 10, 11, 12. And 5, 8, 14, 15, you don't need to provide because it will be the same. But you need to tell that these are the same. And the same for the top plane. And then after that, we need to provide a midpoint coordinate. So the bottom plane view z equals 0, 3 by 3. So we call this the short S span. This will be the vertical, will be the y, the W plane, or the y, and here the horizontal is the x. So we call it S1, S2, S3. The numbering look like this. Then we only need to provide the midpoint which are not in the center point. If a straight line like this one in the middle point, you don't need to provide because it's easy to calculate. It will be a straight line, and the program will know the middle point. It's the sum of the coordinate of one end and the other end, and divide by 2, you get the middle point. But if the middle point is a curve or misplaced, not in the center, then you have to tell to the program where is the location of the midpoint. Let's say a curve, and you identify this. So these are given here, the midpoint. And the same for the W span, or the Y direction. So W5, 6, 7, 8 is a curve. So we need to tell what is the coordinate of that point. So we have the midpoint, the nodal coordinate, the midpoint that's needed, and then we will tell the program actually how we want to divide each of the block. So each of the block you can divide with how many division that you want, let's say 10 or 100 or 200. So in this example, we will take, let's say, 5 division for this block, and the second block, the third block you can define with other, but for simplicity for this example, I just take 5, 5, 5, and the same for the direction for the W. But make sure, even though each block might have a different division in X, Y, of Z direction, but you need to make sure that the mesh have to be matched. For example, a block with side 4 division cannot be merged with adjacent block that have a side with 3 or 5 division. For example, if this is 4, you cannot merge with this one that only have 5 or 6 division. They will not match. And the same for the division in the block in Z direction, in the height direction. Then you can divide, let's say, 6 or 7 or 9 or 10. Then we need to have a rule numbering convention for the side. So let's say these are the cube or the block. So we will name it, the front is number 1, the right side number 2, the back side number 3, the left side number 4, and the bottom is number 5, and the top is number 6. With this defined, then we can tell the program which side to be skipped or to be suppressed from the mesh generation. So you will not generate a meshing on this side and this side because these two will be merged. So block 2, side number 1, 2, so this side will be skipped because it will be merged with block 6, side number 1. And the same with block number 2, side number 1, 2, 3, 4 here on the left hand side will be suppressed, will not be no mesh generation because it will be merged with the block number 4, side number 1, and so on. Now we have defined which side of the block need to be suppressed from the mesh generation. Now we will talk about the automatic generation of curvilinear meshes. So the master element is in real or actual coordinate. Let's say this figure A, and then this master element we will map it into a natural coordinate. So eta and neta, and this will be in the range of -1 to 1, -1 to 1, and it always be a square. So -1 to 1, -1 to 1. So it doesn't matter what will be the real master element in whatever curve or whatever shape. We will map it into this orthogonal square natural coordinate. from minus 1, eta minus 1 to 1, neta minus 1 to 1. And then the division of the master element, we will do also divide it into the same number division in the natural coordinate. Let's say we want to divide by 5 or 6 in the x direction, s direction, or w direction. This will be in eta direction or neta direction. And then after that, we will transform it back into the real coordinate like this. So it's simple to do this interpolation of finding coordinate for the mass here rather than do it directly in the real coordinate. So we will do with the help of the transformation into the natural coordinate and with interpolation of the position in the natural coordinate, and then later transform it back into the actual coordinate. So an example will show it better. So the division of the master element in real finite element is done in the natural coordinate. So here for the interpolation function or the set function, we will use the 8 point, the element serendipity element with X nodal or nodes, boundary node. Start with number 1 from left counterclockwise. Number 1, 2, 3, 4, 5, 6, 7, and 8. And the eta is from ranges minus 1 to 1, neta minus 1 to 1, and the center here will be 0. And then the shape function and derivative. We don't need the derivative here because we don't do any structural analysis or building Slipher matrix. But we just need the shape function here. You can find in most of the handbook or the book in finite element. But these are the shape function we will use for our shape function. Now, how to calculate the transformation mapping? Let's say back to our example. We have we take one block number 2. Let's say this one, and we say divide it by 5 in S span, and W span is also 5 for the block. Then the numbering will be 1, 2, 3, 4, 5, 6 incremental 1 first going in the S direction and go up to the W direction and plus 1 and so on. So you will get from number 1 till number 36 the total of the nodes. And then this one we will map into this coordinate in natural coordinate system, neta and eta and neta minus 1 to 1. So this is a real coordinate and we map to the natural coordinate. And then remember that our shape function is based on this element, serendipity element with 8 nodal numbering on the boundary. So start from 1, 2 in the middle, 3 corner, 4 corner, and 4 middle point. That will be look like this. And these are the coordinates that will be used to do the interpolation of all the coordinates inside this element. In natural coordinate, it's easy to do in natural coordinate. So an example will show like this. So first, the real coordinate. So these are the red one is the local coordinate 1, 2, 3, 4, 5, 6. But remember that our block 2, the numbering is 2, 3, 7, 6. So master 2, middle point 3, and the middle point here, and the local coordinate B. They are just the same. And then we identify the real coordinate. So W3, the midpoint here is easy. It is the sum of coordinate 3 and 5, 3 and 7, the green one, or the red one, 3 and 5, divide by 2, you get the 4, or you get the W3. The same for W2, the sum of coordinate 2 and 6, divide by 2, you get the middle point. But S2 and S5, you cannot do that because it has to be provided, because depend on the curve. It's a half circle of a quarter of the circle, so you have to provide that coordinate. Now, how to calculate the not the natural coordinate of local node number 4 and 9. So if you remember, we have this numbering. So here for this block, the bottom side of the block 2, so these are 4 and 9 divided by 5, so we have end up with 36 nodes. But 4 and 9, how to calculate it? So the local coordinate of node 4 and 9 is very easy, because we start from -1 to 1 when divided by 5. So the eta coordinate of node 4 is this, -1 plus 3 multiplied by 2 divided by 5, because this x of this is 0.4, 0.4. So you get 0.2 here. And the neta coordinate is -1 here. And the same for node number 9. So this will be minus 0.2, and this will be -1 plus 1 multiplied by 2 divided by 5 is minus 0.6, or -1 plus 0.4 is minus 0.6. So these are the coordinate. Once you have this coordinate, then we will do the calculation. So the local natural coordinate eta neta for node number 9 and node number 4, and then we have the set function 1 to 8 here, number 1 to 8. So we have to calculate that function given the eta and neta value. So we get the value of this set function and for each of this coordinate. So we calculate the set function based on eta and neta position from node number 9 and the same for node number 4 we have here, and the real coordinate of the X boundary point, and then local node number 4, the real coordinate is very simple. So this will be this set function multiplied by, for local node number 9 is this, the set function multiplied by the xi here, and for local number 4 will be this multiplied by this x, y, and z. If you have a z coordinate, you can get the same. You can calculate and multiply it and put the ny dot zy. So it works also for 3-dimensional. If you have a different z value, you can put it here. But here is a plan, so the z is always static. And then the sum of these will be the local coordinate for node number 9. So x coordinate, y coordinate, this will be in the real coordinate for the node number 9 and number 4. This is how you calculate and generate all this, the mesh with the nodal coordinate for each small element in the mesh. Now, for the node numbering and the element numbering, so this can be automatically generated from node number 1 to number 6 till number 36 based on the transformation or the mapping that we showed before. And then for element numbering, easy, you just plus 1, so increase one element, one element plus 1 plus 1, so you get an up with 25, 5 by 5, 25 element. And then start again with the next block, the next block on the next side, then you get 26, 29, and so on. Now we have to be careful with the global node numbering, because here node number 6, 12, 18, 24, 30, 36 here actually will be together with this, so they're together, so it should be the same. You should not count with this 37 because they are actually is the same. So this is what we call repeated node at the same edge. So this should be the same. So we should start with, again here, 6, 12, and 37 start from here. Otherwise, if you start 27 from here, actually they are the same. You will end up with 72 instead of 66, the total number of the nodes. So with this, I built the program in Fortran and do some kind of visualization just to make sure that the logic works. You need to have a visualization, a plotting of the generated mesh. Otherwise, you will not be able to detect if there's any mistake or gap in the mesh generation. So with this, I built the program in Fortran with the OpenGL interface, it had the features to suppress the hidden surface, so you can easily rotate and check if there's anything what we model is wrong or not matched with the real structure that we want to model. And there's an option to zoom in and zoom out, rotation, left and right, top and bottom, and then you can also have option to display the nodal number and element number. You can move the object left and right. So with this, I will show you with the simple idea, the concept of the Rubik's Cube. You can use your imagination to create a large variety of structure of 3D surface object or even 3D solid object. So you can use your imagination to set up how many blocks, let's say 3 by 4 by 2 or 6 by 6 by 3, and which one you want to suppress or make it void to cover for the void, for example, and to cover for the curve edge. Then you have to merge the side of the block. So this will be total number of nodes is 440, and total of element generated is 440. And with this one without hidden line or hidden surface, this one with hidden surface enable block. You can rotate from the top. And this is with the opening inside with 4 opening and middle opening. So you can use your own imagination to make the block, which block that need to be void to be able to handle the opening in the object. And this one is a pure solid, only the opening in the beginning, but more element to be generated. This one be more deficient in the master element. And then this one is with the 768 nodes and element also 768. And this will be with the hidden surface option. And you can see this object, a very nice object. It's created. And you can also create it like a donut with 3D view with hidden surface enabled. And you can make a parabol using that cube, how many cube on the top, and then you have the option to suppress the generation of the side of the block. And you can make a water tank, a building, with the zoom in option, and a wing, an airplane, a simple airplane with the cube. And this is generated 3D surface for element 416 and nodal 418. Look like a bridge. And this also a pipe connection. Number of nodes is 2302 and number of element 2208 without hidden surface, with hidden surface, and you can rotate it. And for a cylinder, total number of 1272 and element 1296 with hidden surface. That's it for the presentation. Hopefully you find it useful. And if you have any idea to improve, let me know. Thank you very much.